Welcome to this first video about the best strategies for oxidizing primary alcohols to aldehydes. This video playlist is about the preparation of aldehydes, but most methods can also be used to prepare ketones from secondary alcohols. In this first presentation, we'll have a look at oxidations with oxygen, hydrogen peroxide and hydroperoxides. These are not usually used in laboratory preparations because these oxidations require more optimization than the strategies discussed in part 2, 3 and 4 of this playlist. Oxygen and hydrogen peroxide are, however, the most environmentally friendly oxidants and therefore important for large-scale industrial oxidations. In the other videos of this playlist, I'll discuss scope and limitations of oxidations with TEMPO and other aminoxyl radicals as catalyst, with DMSO and with derivatives of 2-iodobenzoic acid, such as IBX or the Dess-Martin periodinane. The last video is about oxidations with chlorine, hypochlorite, N-haloimides, nitric acid and manganese dioxide. Chromium reagents were important in the past, but are rarely used today. I'll give you a few organic synthesis references, but won't discuss them any further. Most aldehydes are prepared industrially from alkenes and carbon monoxide by catalytic hydroformylation. A few aldehydes are, however, prepared by oxidation of alcohols. These include formaldehyde and glyoxal. Both are manufactured by catalyzed gas-phase dehydrogenation at about 300 degrees Celsius. Acetaldehyde was prepared earlier by hydration of acetylene and is today mainly obtained from ethylene by the Wacker process. Another old manufacturing process is the gas-phase dehydrogenation of ethanol. The preferred production strategy only depends on the cost of these three starting materials, and the chemical industry will always quickly adopt the most economical route. Chloral can be prepared by direct oxidation of ethanol with chlorine. Chloral is the starting material for DDT, but today the required quantities are probably much lower than in the past. Benzaldehyde, by the way, is prepared by oxidation of toluene or by hydrolysis of dichlorotoluene, but not from benzyl alcohol. Most of you have probably seen or performed the following experiment. A piece of copper wire is heated at the air on a Bunsen burner and then thrown into ethanol. The dark copper oxide immediately disappears and clean unoxidized copper wire and acetaldehyde are formed. The precise mechanism of such a heterogeneous alcohol dehydrogenation is as difficult to determine as any chemical reaction occurring on a solid surface. Most of these reactions are likely to proceed by a mechanism similar to the one sketched here. Addition of the alcohol to the metal oxide is followed by beta elimination of the reduced metallic catalyst and formation of the aldehyde. Reoxidation of the catalyst by oxygen can, for instance, occur by initial single electron transfer, followed by the formation of hydrogen peroxide. Hydrogen peroxide is a strong oxidant and will also contribute to the reoxidation of the catalyst, as shown here. Few studies have been reported on the relative rate of alcohol oxidations because these will mostly depend on the type of oxidant chosen. For oxidations by silver picolinate, the relative rate is both a function of electron richness and sterical accessibility of the alcohol, but the rate differences are not large. Allylic and benzylic alcohols are usually oxidized faster than simple aliphatic alcohols. Diols containing both a primary and a secondary hydroxyl group can often be oxidized selectively by choosing the right reagent. Primary alcohols are preferentially oxidized with the aid of sterically demanding aminoxyl radicals as catalyst. Oxidations with derivatives of 2-iodobenzoic acid, such as IBX, or heterogeneously catalyzed dehydrogenations also proceed faster with primary than with secondary alcohols. The selective oxidation of secondary alcohols, on the other hand, can often be achieved with hypochlorite, bromate, or with N-haloimides as oxidants. Let's check some specific examples of alcohol oxidations with oxygen, hydrogen peroxide, or with hydroperoxides. But first, a few words about safety. Reactions with pure oxygen or air and flammable solvents are dangerous and almost impossible to scale up. Thus, it makes little sense to optimize such chemistry at universities on a small scale, arguing that nothing happened. Such oxidations should only be conducted in water or other solvents of low flammability, for instance dichloromethane or carbon tetrachloride. Solvents with a high flash point, such as NMP, diglyme or sulfolane, may sometimes also enable safe oxygen-mediated oxidations. Alternatively, oxygen-nitrogen mixtures with a low oxygen concentration can be useful. Otherwise, batch oxidations with pure oxygen or air and flammable solvents are of little practical applicability. In this example, a primary alcohol was cleanly dehydrogenated to an aldehyde with oxygen and catalytic amounts of palladium acetate. The reaction was, however, conducted in hot toluene, and an explosive toluene-oxygen mixture probably formed above the reaction. Allylic and benzylic alcohols are much easier to oxidize than simple aliphatic alcohols. Here, an allylic alcohol was dehydrogenated by oxygen and palladium acetate. The intermediate acrolein reacted intramolecularly with a sulfene amide. No oxidation of the sulfonyl group or the benzylic positions occurred. Also, copper salts can be used to catalyze aerobic alcohol oxidations. In this example, an enantiomerically pure valine-derived amino alcohol was oxidized to the aldehyde by oxygen in the presence of 5% of a copper complex. Unfortunately, again in a flammable solvent. No dehydrogenation of the tertiary benzylic amine occurred. With inorganic copper salts of low solubility in organic solvents, selective monooxidations of diols are sometimes possible. In this example, with only 1% of copper 2 chloride in toluene, a primary benzylic alcohol was oxidized faster than a secondary alcohol, and a high yield of benzaldehyde resulted. Decanol, however, could not be oxidized completely under these mild conditions. Hydrogen peroxide is a much safer oxidant than air or pure oxygen, as it enables reactions in flammable solvents to be conducted under nitrogen. Here, 1-octanol was converted into octanal by treatment with an excess of hydrogen peroxide and 5% of a molybdenum complex. Early transition metals, such as titanium, vanadium, molybdenum, tungsten, and even rhenium, are particularly good catalysts for oxidations with hydrogen peroxide. These metals do not catalyze the decomposition of hydrogen peroxide into water and oxygen as effectively as the later transition metals. In this example, similar to the previous one, bismuth bromide was used as catalyst. Although bismuth is almost never used in organic synthesis, its derivatives are inexpensive and less toxic than lead, mercury or chromium. Also, platinum can catalyze dehydrogenations with hydrogen peroxide, but seems to be less effective than the early transition metals. Under the conditions of this example, only allylic and benzylic alcohols could be oxidized cleanly. A slight excess of dilute aqueous hydrogen peroxide was enough to bring about a complete conversion. As in the previous examples, the reaction mixture was biphasic and no organic solvent was used. Alkyl hydroperoxides are more miscible with most alcohols than hydrogen peroxide and can also be used to oxidize primary alcohols to aldehydes. Here, 10% of vanadium sulfate was used as catalyst and the reaction was conducted in aqueous acetonitrile. Acetone and acetonitrile are quite resistant to oxidation and thus suitable solvents for oxidation or halogenation reactions. Their flammability, though, precludes their use in oxygen-mediated dehydrogenations. In this example, 2% of a soluble ruthenium complex catalyzed the dehydrogenation of octanol by terzbutyl hydroperoxide. Acetonitrile was again used as a solvent. So, what are the most important potential side reactions? As mentioned, combining oxygen or air with flammable solvents in closed containers is not a good idea. And because larger scale preparations must be run in closed vessels, oxidations with oxygen require either non-flammable solvents or highly diluted oxygen to prevent the formation of explosive gas mixtures. Oxidations with air or pure oxygen can also cause the formation of hydroperoxides. Particularly reactive are benzylic, allylic, and tertiary CH groups. Tetraline, for instance, is readily oxidized by pure oxygen at 70 degrees Celsius without the need of any catalyst. Aldehydes are highly reactive, in particular enolysable aldehydes. If the conditions for their formation are not sufficiently mild, the newly formed aldehydes may decompose in a number of ways. These include by disproportionation, as in the Tishenko or Cannizzaro reactions, and by aldol addition or condensation. When allylic alcohols are oxidized to alpha-beta unsaturated aldehydes, these may undergo retroaldol condensation. Then some aldehydes form rather stable hemiacetals and hydrates. I once optimized the synthesis of an aliphatic aldehyde and always obtained stable mixtures of the aldehyde and its hydrate, what took me a while to figure out. NMR spectra of such mixtures can be difficult to interpret correctly. Then, aldehydes are readily oxidized to carboxylic acids. Such oxidations usually proceed by hydride abstraction from a hydrate or hemiacetal and may proceed more slowly under strictly anhydrous conditions. In this example, 1-heptanol was oxidized with an excess of hydrogen peroxide and catalytic quantities of sodium tungstate. The main product was heptanoic acid. Here are some more, mostly recent examples which you can also find in the description of this video. Part 2 of this playlist is about oxidations of primary alcohols with aminoxyl radicals as catalyst. These are easier to perform than aerobic oxidations and better suited for laboratory preparations. See you then.